Welcome back. We're now in 8.2, hybrid atomic orbitals. In this section, we are going to explain the concept of atomic orbital hybridization and determine the hybrid orbitals associated with various molecular geometries. So, valence bond theory is great and all, but it has to be modified to explain the covalent formed in molecules that have more than two atoms. It's great for when there's only two atoms, but once we add more into a molecule, it kind of falls apart. For instance, water. Okay, the oxygen in the structure of water, so far what we've seen it looks like using VSEPR theory is something like this. The oxygen has those two unpaired electrons that are in the 2p orbital. So valence bond theory would predict that these 2p electrons overlap with 1s orbitals of hydrogen, and then which results in a 90-degree angle. But from experimental data, we found that the bond angle is actually a 104.5 degrees. So valence bond theory does not match, and we need to use a different model. Quantum mechanics, so we're going back into quantum mechanics a bit. What it suggests is that the wave function, so remember those psi's, okay, these things, combine. So the wave function of the oxygen and the hydrogens are combining to produce differently shaped orbitals in a process called hybridization. So yep, chemistry has hybrids. Not like the biology hybrids, chemistry hybrids. So the resulting orbitals are called hybrid orbitals. So to give more accurate predictions using valence bond theory, we need a hybridization component. So this is what valence bond theory would predict for the structure of water. With the overlap, it would predict this bond angle of 90 degrees when the 1s orbitals of the hydrogens overlap with the 2p lobes of oxygen. But we don't actually get that 90-degree angle. Does not happen. In reality, the angles look like these ones here. In A, this is showing the all the areas of electron density and the tetrahedral arrangement that we get from VSEPR theory. And then we see the 1s orbital overlap from hydrogen in the second picture, and it's showing the actual angle. So VSEPR theory would predict a 109.5 degree angle in water, but in reality it's around 104.5. So bonding in other molecules is best explained with hybrid orbitals. And this is something, I think it's really good to at least give you an introduction to this stuff. One of the reasons that I still wanted this in this class is because for those of you, which should be most of you, that are going to be going on to organic chemistry after general, hybridization is very important in organic chemistry in structures. So you're going to constantly be talking about sp3, sp2, sp type bonds. So there's some things to know when you're working with hybrid orbitals. They are only formed in covalently bonded atoms, so they're not in ionic compounds. They have shapes and orientations very different from atomic orbitals of just the atoms. Okay, so you can't look at an atomic orbital and go, okay, this is what the hybrid looks like. They're very different. The number of hybrid orbitals formed always equals the number of atomic orbitals that are combined. All orbitals in a set of hybrid orbitals are equivalent in shape and energy. Okay, their orientations may be different, but their actual shape and the amount of energy that's associated with them are the same. And the type of hybrid orbitals formed in a bonded atom depends on its electron pair geometry as predicted by VSEPR theory. So you still need VSEPR theory. Very, very important that you don't just put it out of your head. And hybrid orbitals overlap to form sigma bonds. Unhybridized orbitals overlap to form pi bonds. Okay, so pi bonds do not contain hybridized orbitals. They are regular orbitals. It's the sigma bonds, those single bonds, that have the hybridization about them. So let's talk about the hybrid orbitals. The first type is the sp hybrid orbital. So if you have two atomic orbitals, they can hybridize to form two hybrid orbitals. So you have one s orbital and one p orbital. These will hybridize to form two sp hybrid orbitals. So this happens when you have a central atom surrounded by two regions of electron density. And those valence electrons are going to occupy newly created hybrid orbitals, and this has a linear geometry. So like I said, VSEPR theory still comes into play here with the electron density, the two regions, and the linear geometry. So something like carbon dioxide. Okay, linear geometry still. So this is kind of what the orbitals look like. You have here, this is your s orbital with the p orbital, and they form these two hybrid orbitals. Notice they have these little tiny lobes and then a bigger lobe. And a lot of times we kind of ignore the small lobes just for the sake of space, but they do actually exist. But then it turns into, when you put everything together, it looks kind of like this guy with a 180-degree difference between the two lobes. So there's your linear arrangement, just like we talked about in VSEPR theory. Now, the other thing that happens is you form these new, oh gosh, where's my words? You form these new energy diagrams. So if we're looking at a beryllium atom in BeCl2, beryllium has two electrons in its 2s valence shell, but when we form our hybrid orbitals, when it bonds with chlorine, what ends up happening is these two electrons, one goes to each spot in the energy diagram. Since they're degenerate orbitals, that means they have the same energy. That means, remember, we always do one electron in each orbital first, as that's lower in energy than pairing them and then having one lobe open. So then you can see now we have unpaired electrons for those chlorines to then bond with. Okay, so that was sp. And the next is sp2 hybridization. So this is where you have three atomic orbitals hybridizing to form three hybrid orbitals. So one s orbital and two p orbitals, making three sp2 hybrids. So this is when you have a central atom with three regions of electron density and a trigonal planar geometry. So this is what this hybridization looks like. Your s and you have two p orbitals, a px and a py. So notice our x-axis is here, this is y, and that's z. So we have one p orbital, a px orbital, and a py orbital. So then we get this trigonal planar hybrid that results from the overlap. And this is an alternative way of drawing it. Notice you kind of have a little node there in the center as well. Boron trihydride is an example. It's an electron deficient molecule, but it has that trigonal planar structure. And if we were to look at an isolated boron atom, this on the left is what its orbital diagram looks like. There are 1 2s and 3 2p valence orbitals. Okay, so we have a filled 2s orbital at first, and then just one electron in the 2p. But when we hybridize, we take these three electrons, and now we have three unpaired electrons in this sp2 hybrid lobe that are now available to be paired with the unpaired electrons from hydrogen. And these are some other examples of sp2 hybridized structures, or they have that central atom that is sp2. We're all talking about electron density, so lone pairs still count. So all these structures here, including these carbons, each of these carbons are sp2. Okay, this guy's sp2. All of these central atoms are all sp2. Next is sp3 hybridization. And when you go on to organic chemistry, this is the one that you're going to see the most. sp3 and sp2 tend to be the hybridization that you deal with the most, sp3 being the most common. So this is when you have 4 atomic orbitals hybridizing to form 4 hybrids. So 1 s orbital and 3 p orbitals to form 4 sp3 orbitals. And notice for all of these, it was that 1 s orbital with however many p orbitals. So that's where the s in the sp part, and then the p, of course, and that number there tells you how many p orbitals. So your central atom here has 4 regions of electron density around it. So tetrahedrals. So here's the hybridization here. You end up forming this tetrahedral arrangement. I don't know why this thing keeps saying purple here. Yellow. So here's the hybridization for a carbon atom. Isolated, it has a 2s and the 2 electrons in the 2s and 2 electrons in the 2p orbital. But when hybridization happens, we take those 4 electrons and we have 1 in each sp3 hybrid orbital. And now it can pair those electrons to bond. So another example, this is the ethane molecule. And ethane is 2 carbons, each with 3 hydrogens on them. So this is C2H6. Each carbon is an sp3. Notice they each have 4 areas of electron density around them. The other thing that happens with sigma bonds is rotation. So they can actually rotate around sigma bonds. So single bonds are able to rotate freely. They don't break, but it just goes in circles, and those atoms are then rotating along this axis. Next, a not as common hybrid is the sp3d hybrid orbital. So this is 5 atomic orbitals making 5 hybrids, 1 s orbital, 3 p orbitals, and 1 d orbital. So sp3d. This is when you have 5 regions of electron density. Here are some examples. Sulfur tetrafluoride. This chlorine tetrafluoride is supposed to be an ion, I believe. Oh, no, never mind. But nonetheless, all of these, that's chlorine trifluoride, don't mind me, are on the central atoms. These are all sp3d central atoms. That's our hybridization here. So this is kind of what they would look like in 3D. This is phosphorus pentachloride. So it's got the 5 sp3d orbitals to form a trigonal bipyramidal structure. And then we also have sp3d2. So as the names kind of states, 1 s orbital, 3 p orbitals, 2 d orbitals, making 6 sp3d2 hybrids. So this is when your central atom has 6 regions of electron density around it. And here's an example. Sulfur hexafluoride has its octahedral, with those 6 regions of density around it to give it this hybridization. All right. Now, when it comes to assigning hybrid orbitals to our central atoms, we have some steps to take. But it's, first of all, determined by the number of regions of electron density around it. So just like we've done electron pair geometries predicted with Vesper theory. Same kind of general concept. So to determine hybridization, first, Lewis structure. Then figure out the regions of electron density using VSEPR theory. And then you can assign your hybridized orbitals that correspond to that geometry. Couple things though, when you have a larger central atom, you have less hybridization because you now have less repulsion of the electrons being closer to each other. Okay, so for instance, this is oxygen, sulfur, and oh gosh, what's the last one? Well, we're going down underneath oxygen. And as we go down the periodic table, our atoms are getting bigger, right? So what's happening now is you have this bigger central atom, and because of that, you're leading to a bigger overall angle. Now these electrons aren't having to be repulsed by each other as much because they have more space. So we have less hybridization as we go along. So as you see, our third guy over here has a 90-degree angle, like VSEPR theory would predict, like VSEPR and valence bond theory. But oxygen and sulfur still have that hybridization, oxygen especially. So your book gives you a nice little table here with the regions of electron density, their arrangement, and then the hybridization. So you figure out how many regions of electron density you have, and then from there you can get your arrangement and what the hybridization looks like, including the bond angle. So notice for like trigonal bipyramidal, you have 90 degrees and 120 degrees. Two different angles. So let's look at an example. Ammonium sulfate is a very important fertilizer, and we want to know the hybridization of the sulfur atom in the ion. So our Lewis structure would be the first thing to draw. I think you guys are pretty good with Lewis structures. So this is what it looks like. You have the sulfur surrounded by 4 oxygens. And so when we look at this, we have 1, 2, 3, 4, or just if you wanted, by the way, O. Okay, so we see these 4 areas of electron density. So since it's 4 areas of density, that means it is sp3. The next one, the hybridization of selenium and SeF4. So we would go draw our Lewis structure and we get this guy shown below. And we see 1, 2, 3, 4, 5 areas of electron density. So that means it must be sp3 dehybridized. Another example, urea, NH2CONH2 is sometimes used as a source of nitrogen in fertilizers. What is the hybridization of each nitrogen and carbon atom in urea? So we have 2 nitrogens and 1 carbon atom. Notice the nitrogens are the same, so we can really just look at one. So we look at one of these nitrogens and we see 1, 2, 3, 4 areas of density. So that means our nitrogens are sp3. And the carbon here has 1, 2, 3. So carbon is sp2. One more example, acetic acid. This is what gives vinegar its odor and taste. And let's figure out the hybridization of the 2 carbon atoms. And maybe we'll do the oxygen because why not? Let's get crazy. So let's start on the left carbon. We see 1, 2, 3, 4 regions of density. So that is sp3. Central carbon here has 1, 2, 3 regions of density. So it is sp2. And the oxygen has 1, 2, 3, 4 regions. So it is sp3.